Hello everyone, this is Sanjay from CSIT branch. Today my AAT Tech Talk topic of theory of computation is model learning. So first we are going to discuss about what is meant by model learning. It is unlocking the mystery. Model learning is a powerful technique to create models of black box systems. This presentation discuss how to apply model learning to hardware and software components that are difficult to understand and how to unlock the mystery behind them. Why is model learning? The benefits of model learning helps us understand complex systems that can identify errors and vulnerabilities in hardware and software components. So we routinely manage to learn the behavior of devices or computer programs by just pressing buttons and observing the resulting behavior. Especially children are very good at this and know exactly how to use a smartphone or micro oven without ever consulting a manual. In such situation, we construct a mental model or state diagram of the devices. Through experiments, we can determine in which global states the device can be and which state transitions and outputs occurs in response to which inputs. This article is about the design and application of algorithms that perform this task automatically. There are numerous approaches where models of software components are inferred through analysis of the code, mining of system logs. Yes. Many different types of models are inferred, for example, hidden Markov models, relations between various article we focus on one specific type of models, namely state diagrams, which are crucial for understanding the behavior of many software systems, such as security and network protocols or embedded control software. Model inference techniques can be either white box or black box, depending on whether they need to access the code in this article. We discuss about the black box techniques. Advantages of these techniques are they are relatively easy to use and can also be applied in situations where we do not have access to the code or to adequate white box tools. As a final restriction, as a final restrictions, we only consider techniques for active learning, that is, techniques that accomplish their tasks by actively doing experiments on the software. There is also an extensive body of work on passive learning, where models are constructed from the sets to runs of software. An advantage of active learning is that it provides models of the full behavior of a software components, and not just of the specific runs that have occurred during actual operation. The fundamental problem of the active black box learning state diagrams has been studied for decades. In 1956, Moore's first and the key insights are model learning aims to construct black box state diagram models of software and hardware systems by providing inputs and observing outputs. The design of algorithm for model learning constitutes a fundamental research problem. Recently, much progress has been made in the design of new algorithms, both in a setting of finite state diagrams, that is, Mealy machines, and in richer settings with data register automata. Through the use of abstraction techniques, these algorithms can be applied to complex systems. Model learning is emerging as a highly effective bug-finding technique with applications in areas such as banking cards, network protocols, and legacy software. And this is the about model checking and the Mealy machine. The Mealy machine is a tuple consisting of the m equal to I, O, Q, epsilon, and lambda, where I is a set of inputs, O is the final set of outputs, Q is the final set of states, and Q naught is an initial state, and the Q into I is an transition function, O is an output function, and it is a simply Mealy machine. Here we can see about initial state, final states, and the inputs and outputs going through the Mealy machine. Propose the problem of learning finite automata. Propose the problem of finite automata. Provide an exponential algorithm and prove that the problem is inherently exponential. The problem has been studied under different names by different communities. Control theorist refers to it as system identification computation. Linguists speak about grammatical inference. Some papers use the term regular inference, regular extrapolation, or automata learning. and the security researchers coined the term protocol state fuzzing. Here we will use the term model learning in analogy with the commonly used term model checking. Whereas model checking is widely used for analyzing finite state models, model learning is a complementary technique for building such models from observed input and output data. In 1987, Anglin published a seminal paper in which she showed that finite automata can be learned using the so-called membership and equivalence queries. Even though harsher algorithms have been proposed since then, the most efficient learning algorithms that have been applied today all follow Ang- Anglin approach of the minimally adequate teacher. And these are some of the Mealy machine. And next we are going to see about the Anglin algorithm. Elster algorithm incrementally constructs an observation table with entries taken from the set O of outputs. The rows are labeled by words in S union of S, I, where S is a non-empty finite prefix closed language, and the columns by a non-empty finite suffix closed language E. Formally, an observation table is triple S, E, and row, where row is S union of S star I, where for a given prefix W suffix C. Row WE returns the last output produced by the SUL in response to the membership query. Initially, S only contains the empty word epsilon and E equals set of inputs I. Two crucial properties of the observation table allows for the construction of Mealy machines, closedness and consistency. Observation table is closed for all W belongs to S. If there is W not belongs to S, its row W, it has a consistence of whenever row to some W and W belongs to S. And first table of the S hypothesis. Model learning with the MAT framework, and this is here we can see the diagram of the model learning with the MAT framework, and this is the model learning with a mapper. Examples of these applications. During recent years, model learning has been successfully applied to numerous practical cases in different domains. There have been industrial applications, for instance, on regression testing of telecommunication systems at Siemens, on integration testing at France Telecom, on automatic testing of an online conference service of Springer Verlag, and on testing requirements of the brake-by-wire system from Volvo Technology. Below, I review some of the representative case studies that have been carried out at Radboud University related to smart cards. Smart cards used model learning to reverse engineering the identifier as smart card reader for internet banking. To be able to learn a model of identifier, the authors constructed a Lego robot controlled by a Raspberry Pi that can operate the keyboard of the reader. Controlling all this from a laptop, they could use LearnLib26 to learn models of the identifier. They learned a four-state Mealy machine of one version of the identifier tool that revealed the presence of a security flaw, and showed that the flaw is no longer present in three-state model for new version of the device. Others, then this is the example that the Lego robot is designed by model learning by reverse engineering, and in this Raspberry Pi is used. Network protocols, a society has become completely dependent on the correct functioning of network and security protocol. Bugs or vulnerability in these protocols may lead to security breaches or even complete network failures. Model checking has proven be an effective technique for finding such bugs and vulnerability. However, since exhaustive model checking of protocol implementation not feasible, model checking is usually applied to models that have been handicrafted starting from protocol standards. This meant that model checking is unable to catch bugs that arise because implementations do not conform to their specific creations. Model learning turns out to be effective in finding exactly these type of bugs, which may technique complementary to model checking, and it is the state machine of source code or application of the Dutch Robobank card diagram. And this is the learned state machine of Windows 8 TCP client. And it is the approach of the compare legacy component and refer to implement courtesy of the shut set all. And it is the register automation. Abstraction is a key for scaling model learning methods of realistic applications. Even though model learning has been applied successfully in several domains, the field is still in its infancy. So state machine models are a powerful way to represent the behavior of the hardware and software components. They can be used to model complex systems and create test cases of the verify correctness. Black box models are models of systems that we do not fully understand. Model learning can be used to create black box models that capture the behavior of the complex hardware and software components. Applying this of the model learning can be applied to hardware and software components to create models that capture their behavior. This can be used to identify errors and vulnerabilities, optimize performance, and reduce cost. Conclusion: I finally conclude that model learning is a powerful technique for understanding and optimizing complex systems. By applying model learning to black box systems, we can unlock the mystery behind their behavior and create models that help us to identify errors, vulnerability, opportunities to the improvement. Thank you.